item response theory is something that's really cool when you have the opportunity to do it, and the situations where you're most likely to have the opportunity to work with this is if you've got a test where you're administering that test to at least 300 people, because it's going to take 300 people to be able to do a one parameter model. But you know, if you've got situations where you have 1,000 or 1,200 or 10,000 people, I think it's a really good approach to use, because you get a lot more item-specific information out of this that you can use to try to calibrate items instead of just determining whether, like with classical true score theory, that is, you know, looking at biserial correlations and difficulty levels and discrimination index, you know, you try to figure out whether that item works within the context of the test. Well, with item response theory, what you're doing is you're disembedding that item from the test. Of course, you have to have the rest of the test data. Tater test? Okay, it's getting light. Tater test, that sounds like something that Sonic would serve, right? We got fried tater tests. Okay. You're disembedding that item, and you're looking at that item in terms of how it relates or how well it measures different levels of your latent construct. So that was that theta thing, you know, using the good old Greek letter theta. And what happens is that, theta represents the underlying what, the construct, or whatever it is you're trying to measure with that item. And what happens with item response theory is, here's the level of theta. So in other words, theta could be anything. It could be job knowledge, it could be introversion, extroversion, it could be conscientiousness. You know, you could have some kind of individual weirdness feel, whatever it is you're attempting to measure. And as the amount of whatever that is that you're trying to measure is possessed by examinees, it gives you the probability that people will endorse the item in the keyed direction. Now, this is kind of an important distinction that a lot of times when we're working with tests, like selection tests, we're talking in terms of, did people have the right answer, or did they have the wrong answer? Well, if you think about personality measures, right? Introversion, extroversion, conscientiousness, those things that Joe Tomacic likes to work with, there really isn't a right or wrong answer, right? That we're looking for people that endorse items that indicate that they're introverted or extroverted or whatever it is we're trying to measure. And the more of, let's say, for example, introversion, somebody would possess, the greater the likelihood that they're going to endorse that item in the key direction that indicates introversion. Okay? So this little function shows up over and over again in the social sciences and economics and psychology. And if you look at something called psychophysics, that same kind of function, the Weber-Fechner laws, and some of those other discrimination function ideas, it shows up. Well, classical test theory, difficulty level, discrimination level, the two we just talked about, and then that reliability, that is, you know, is the test consistent or the subtest consistent in terms of the types of scores they produce, time one, time two, or do those items intercorrelate, like with the Jerry test, the verbal and the quantitative items, they intercorrelate. Right? So classical analysis uses the whole test and not the item. Okay? And this is where item response theory is really cool, because again, what it tries to do is it looks at each individual item. So in other words, I can't really interpret, I can't have a discrimination index without having the other items. Okay? But with item response theory, I can do something that's called, calculate the discrimination parameter, which is the point at which people are 50% likely to endorse that item in the key direction without even considering other items. So we've got something called local independence. So I can look at items individually without considering other items. And that's one of the objective questions that I have from that sheet that I posted. Local independence. With classical true score theory, classical test theory, there's no local independence because we're considering each item in the context of the test. Okay. So the discrimination index, or the biserial correlation in the context of the test, right? So I can't have that discrimination index without considering the whole test. I can't look at reliability without the whole test. Item response theory, latent trait models that look at the underlying traits, that's this theta, and how different levels or how increasing levels of that underlying trait increase the probability that somebody's gonna endorse that item in the key position, the key direction, or give the correct response. And as such, you're disembedding the item from the sample and just looking at the item as kind of a standalone thing. That make a little bit of sense? Been around since the 1940s. Again, part of the reason why we see more activity with these abstract models now is we all have software. We can do this stuff fairly easily. 1940s, hand calculators, mechanical calculators. What was the first operational computer? The Sperry-Rand Univac, which was made out of vacuum tubes and took up an area about, I think Tillman said, about 3 times the size of this room. And it had all the power of a handheld calculator. Or if you consider the Apollo 11 astronauts went to the moon, and the total computing power they had was something like 12 kilobytes of memory. Okay. So, you know, wouldn't even be able to use the Apollo 11 through 17 computers to be able to do this. Now, you know, we damn near do this on our phones, but certainly with the software. So, theoretically possible, but more practical because of software. The aim is to try to identify the degree or the how much of that underlying trait is going to change performance on an item, with the idea that we're going to do something where we disembed that item from the sample and disembed it from the test and look at it individually. And kind of like factor analysis, there isn't one procedure, but there's a whole lot of different ways of calculating this. If y'all want to mess around with this, like after the end of the quarter, or between now and you know, the end of days, whenever that happens, right? There's all kinds of free software out there that you can find on Google to be able to perform IRT. It's kind of interesting. There's not enough people doing this commercially for them to make a ton of money off of this, but the people that support a lot of this stuff are interested in providing free software. And of course, you can do the stuff with R too, if you like. I'm not a big fan of R like Patty is. It tends to be buggy. I kind of wuss out and go back to SAS or something I'm familiar with. So, okay, so we have classical true score theory, and IRT gets referred to as modern psychometric theory, modern test theory. And in terms of applicability, if you're dealing with numbers less than 300 examinees taking a test, chances are you're going to have to use classical true score approaches. You're going to have big numbers and wide scale, or, you know, big N testing to be able to work with item response theory. But if you can do it, it has a lot of advantages. So some of the things that work or that you can do with this is that item response function, and that's what this curve is. So we come up with a mathematical formula that explains or describes how levels of that theta correspond to people's ability to either provide the correct response or endorse the item in the correct key, using the correct key response. The item information function. So that's part of what happens with that curve is that, let's say we've got an item that does something like this. That's not functioning as well as the item that does this other function. And in a perfect world, what you'd have is an item that was like this, where, you know, at a certain point, boom, everybody gets it right. It perfectly separates people. Well, not the real world. What you have is this normal ogive. What that normal ogive is kind of like a bell curve that only goes in one direction. This idea of invariance, position on the latent trait that can be estimated by any item. You know, we know the item information function with respect to the characteristics of the population. So in other words, the item isn't being, at least by the time you've done the calculations, the item or the response information isn't being influenced by other responses, that each one of those items are being looked at independently. So item response function, again, characterizes the relationship between that theta and endorsing the item. And as such, what should happen is that relationship between, you should be able to come up with a fairly consistent calculation in terms of people's proportion, or how much of that latent trait they possess, and their ability or likelihood of endorsing the item correctly. Now, examining trait level, oops, grade should be capitalized, right? It's proper now, sorry about that. Letter theta, and then typically has a mean of 0 and a standard deviation of 1. Okay. So in other words, what's being graphed here is if we're going to plug in what is that we're scaling this on. If you look at what's happening here, 0 would be the mean, and we would be looking at how much relative to the rest of the population, the proportion of theta that somebody possesses before they're going to endorse the item in the correct direction. Is that enough to get started? You all want to work. I'll do a couple more slides. I'm going to go. We'll take a look at a couple graphs, and then we'll end there. And then I'm going to turn you all loose with the activity sheet. And I'll be like, okay, we got out of class early, but the bastard gave us all this other stuff. The item functions are graphically represented using the item characteristic curves. And just kind of give you a little heads up in terms of what can happen with this stuff. So with those item characteristic curves, we can examine something called differential item functioning. What differential item functioning is where an item works differently in one group than another. And when that happens, you have to ask, okay, what's happening with this item where it's working differently in this other group? So let's say, for example, this is, and this, I'll relate this to something that's happening here where people are working with that STEM project, right? And what's one of the things that happens with STEM? What are we trying to do with STEM? What's the purpose of STEM? Science, technology, engineering, math. Okay. Particularly who?
Not the normal people,
One of the policy aims of STEM is to attract a certain group, and what is it?
Underprivileged female.
Yeah. So what we're trying to do is, with respect to the people that are involved in science, technology, engineering, and math, the United States is a relatively small country. We've got 330 million people. And to be able to do what we need to be able to do, we have to make sure that we're maximally using human resources properly. Actually, just about every industrialized country on the planet is working on this too, that we need to draw more people into science, technology, engineering, and math to kind of make human history move forward. So who's being underutilized? Women. And what happens when women take certain types of standardized tests? They don't perform as well on math. And for a long time, the thinking was, well, men tend to be left hemisphere dominant, which is not really true. And men tend to be better at math, in which we say, oh, we look at it now and say, okay, there's no genetic or innate difference present. We've studied all this. So then we look at what's happening with the part of the population that isn't participating, and something's happening with respect to what comes out of education or testing. So where I'm going with that is, let's say this is a math item, okay? And this line represents men, and this line represents women. As we all know, women starts with an F, right? Okay. So, yeah, okay. Make myself a little bit more consistent, male and female. Okay. Well, what's happening here? If you see what's happening here with, if this is one item, men can have less of whatever it is that item is asking and still get the item in the correct key position. Women have to have more. So we have this area of what we call latent space, where we have differential item function. And this is what's really cool about IRT, is we can spot stuff like this, and then we can back up and take a look at that item and say, okay, why do women have to have more of this to be able to get the correct keyed response? And then maybe we can identify something within that item and say, okay, in terms of how we're asking this in a way or using metaphors or analogies or idioms that men are more likely to understand. So it's kind of failing in terms of what it is supposed to be doing as an item, where what we're gonna try to do with this, to try to get this item correct, is we're gonna make, as much as possible, make sure that both of those lines look the same, okay? So that's what's kind of cool about IRQ. It's one of the things that's cool, so we can do this kind of item calibration. And with that example, I mean, we could take any two subgroups. We could take whites and African Americans. We could take old people, young people. We could, you know, any two groups. And the idea is that we can examine each item to make sure that the item characteristic curves are giving us equal and consistent measure. Okay. I'll back up on this, but let's take a look at some of the curves here. Okay. So the discrimination point here, with an item characteristic curve, that's going to be the point at which 50% of the people are endorsing it correctly and 50% are not. And what you try to do is identify whether that occurs, and again, these are standard normal deviance. So is it occurring at the average, is it below average or above average? Okay, so that's your location. So location and discrimination. With the perfect item kind of being like, sort of like this illustration here, where the 0.5 is occurring with essentially what's going to be the 0.5 or the 50% point that is right at the mean or the median within the normal distribution. Now, this is that example I was presenting where you have the same discrimination function, but different locations. So in other words, whatever population 2 is, population 2 has to either know more or possess more of that latent trait or construct of interest to be able to get the item correct or endorse it in the key direction. In this example, if let's say this was with 1,200 people, this wouldn't be that big of a deal. But when that separation becomes really pronounced and it occurs over and over again, that's where you start asking, okay, what's going wrong with these items? Why are they why is this item functioning different in two different populations? Okay, this example here, this could also be another example of differential item functioning, where we have different discrimination, that is the curves are different, but, and different locations, okay? So this would be another example of why is this occurring differently in two populations. This could also be an example of two different items too, but you know, when I've used this before, not usually comparing item to item, but looking at what happens within two populations with the intention of making sure that the item is functioning, or if the item's going to be retained, it's going to function the same within two populations. Okay, that's where I'll stop for tonight with this. If you all would take a look at the videos and the other resources, and we'll pick up with some of this, and we'll finish off with some factor analysis next week.